Hi, everybody. This is Aaron Schwartz, one of the secondary math specialists with Montgomery County Public Schools. In today's screencast, we're going to be looking at bike lovers, which is actually the second lesson of Unit 5 of our current Algebra 1 curriculum. Bike lovers is a great little sequence of lessons because it allows us to start exploring continuous piecewise functions and actually helps us move into absolute value, step, and other function types. So in this screencast, what we're going to be doing is looking at a small piece of that bike lovers lesson, and then we're going to be using it to spring into some Desmos exploration to help solidify things that we've noticed. In Unit 5, the students learn about square root, cube root, absolute value, step, and piecewise functions by exploring patterns in diagrams, tables, and graphs. Some of the key ideas include that a piecewise function is composed of pieces of other functions, expressed over their own unique domains. The rules for transformations of quadratics are the same for all function types. And because of that, linear functions in point-slope form reveal the transformations of those functions. Some of the helpful skills that students already have coming into this unit include that linear functions in point-slope form reveal a particular point that is contained within the line and the slope of that line. That's explored in Unit 2, Topic 2. Linear functions in point-slope form follow the same transformational rules as quadratic functions in vertex form. And that's something that comes up in Unit 2, Topic 2 with respect to the linear functions, and Unit 4, Topic 2 with respect to the quadratic function. And in this unit, we'll be putting those together. So the bike lovers lessons are very interesting, and they go through a series of continuous piecewise functions. And the functions that are explored in this unit or in this lesson are all linear. And what I've done in this particular screencast is focus on one particular piece that I think is very, very salient. If students at this point have not had a really good exploration of point slope form because it was skipped in Unit 2, Topic 2, they're going to be at a real disadvantage. That's a very important lesson from that particular topic. And it's worth going back and exploring either if students didn't have that learning or if students had that exploring and that learning, but they need some refresher. Now let's go through the video as though students have that mastery and that understanding of point slope form. We would give this particular function to students, and one of the first things we would ask them to notice or ask them to describe is what they see in this particular piecewise function. Now, students may see a bunch of different things, and it's important to get as many of those things out, no matter how low the level of the observation is. For example, students may notice that all of the slopes are fractional. That's really important. Students may start to notice some other things, such as all of them are linear. Again, it's lower level, but it's really important that students articulate that and really hone that out before they move further into their noticing. One other thing that students may notice is that 3 of the 4 different expressions are in point slope form. Now, this is a good time to refresh students on what point slope form is. Typically, we express point slope form as y equals m times the quantity x minus x1, end quantity increased by y1. Now, that's a perfectly valid form. It's only convention that has us use x1 and y1. What we can actually do at this point is say, you know what, we've had this vertex form of a quadratic, so let's make this point slope form a little bit more like what we just learned about in the quadratics unit. We're going to change x1 and y1 to just h and k. This becomes a really important noticing moment for students because what they may say is, so a point slope form is really the vertex form but not squared. And in fact, that's a very accurate description. What they're really saying is that linear equations are a degenerate case of quadratic equations, and that the point slope form is a degenerate case of the vertex form of a quadratic. From here, we can start moving into some things. So students may notice a bunch of other things, particularly with the domain pieces and the expressions. So one of the key things that they may notice is that the end of one segment becomes the h value in the expression of the next segment and the first domain value of that next piece. So for example, 1/4 t, the domain ends at 20. 20 is essentially the h value in the next expression, and it's the beginning of the next domain increment. The same thing is true with 50. 50 is the end of the second domain increment, but it is the h value of the third expression. It's also the beginning of the domain for the third expression. Now, because of this, we can ask students to make a hypothesis that we'll validate later. And the hypothesis is, what's the value of A? Well, based on the pattern we've seen, it's a valid hypothesis if students say, oh, A has to equal 92. Now, at this point, we're going to tell students that that's our hypothesis. We don't know for certain, but we're going to try and validate that later. So another thing that we'd want to do is change that 1/4 t. We want to change that into point slope form just to illustrate a few concepts later. So we're just going to change that to 1/4 the quantity t minus 0 plus 0. And again, this is to highlight some things later. Now at this point, we may have noticed all the things that we can just by looking and examining this function d of t. So what we want to ask students to do is calculate the value of the last domain value for each segment. So for example, d of 20 is equal to 1/4 20 minus 0 plus 0, which is 5. Let's do the same thing for each segment. So in the next segment, I want to do the d of 50, the distance at 50 seconds. So d of 50 equals 1/5, 50 minus 20 plus 5. That's going to be 11. The same thing is, we're going to do the same thing with 92 and the third segment. So d of 92 is 2/7 times the quantity 92 minus 50 plus 11 equals 23. Now, before we go any further, this is one of the few places where we want students to just grab a calculator and calculate, because it's not the calculation that's important, it's the result of the calculation that we really need students to spend their time noticing. And already we may be able to see some connections. One of the things that students may notice is that d of 20 is 5, which happens to be the k value in the second segment. D of 50 is 11, which happens to be the k value in the third segment. And d of 92 is 23. And at this point, we can make a hypothesis about the value of b. We can hypothesize that b is 23. Now again, we want to stress to students, we're going to validate this hypothesis in a moment. We don't know for certain yet, but already we've seen some very interesting patterns evolve. So the next thing I want to do is actually go to that bike lovers Desmos graph, because that bike lovers Desmos graph is really going to help us solidify things. All right, so here we go. And we'll come back to that presentation in a minute. This bike lovers graph is based on the equations and expressions we just saw. And so you'll see in the left-hand side, I've got that 1/4 x, that 1/5, the quantity x minus 20, and so on. Desmos does some really nice things. What it allows us to do is restrict domains, which is why I have these curly brackets. These curly brackets allow us to define a domain over which this particular expression is graphed. Now, one of the things I did in the lesson was I changed 1/4 x, or 1/4 t actually in the lesson, to be -0 and +0. This is really interesting because I now see 0, 0, and I see that the point 0, 0 is in fact part of the graph. It is the first value that is graphed in this expression. The next thing that I'm going to see is that we have this point at 25. And if I look at my second expression, I see the numbers 25. So what's actually happening in this lesson sequence is that we see that with linear equations, it doesn't have to be the vertex. It can be any point along the line, and we keep defining each of the linear segments using the initial point. The same thing is true on the third one, 50 and 11, 50 and 11. And now we have to figure out what we're going to do for A and B. So let's go ahead and let's actually test the point. And let's see if what we predicted works out to be true. When we originally did things, we suggested that A should be 92. Well, it looks like 92 really lines up with the end of that graph, but we have this vertical jump. But just to make sure, let's change A. Well, as we change A, we notice that we would be under this domain segment, so that's not going to work. Let's go ahead and change it back to 92. Now, we hypothesized that B, 23, would be the right value for our K. So let's go ahead and let's play around and let's just kind of move B up and down. And when we move B up and down, we can see that we get closer as we move the value up. But it's not until we change it to 23 that the graph actually becomes a continuous linear function, a continuous piecewise linear function. And so one of the key learnings from all of this is that that point slope form is incredibly useful. And it's incredibly useful because if we want a line to start at a particular point on the coordinate plane, we can use that point to define our line, define the slope that we need, and then we can just graph it. Now, Bike Lovers is the bridge point to a lot of other learning. So I'm actually going to do a new graph. And we're going to do an absolute value. One of the things that Bike Lovers allows us to do is to start to look at absolute value functions in the context of two pieces. They are, in fact, a two-piece continuous piecewise function. But there's another way to explore it that is absolutely in line with everything students have learned. In fact, if we treat absolute value functions just like a quadratic, a, h, and k, one of the first things that students can notice is that there's a vertex just like a quadratic. One of the other things that they can notice is that the vertex is whatever h and k are. So if I move h to be over here somewhere, 3.2, sure enough, my vertex has a domain value of 3.2. If I move k to be negative 3.4, sure enough, that's exactly what my vertex is going to be. So this has become a very valuable launching point into understanding how those transformations apply to all graphs. Just like A, we can talk about it moving the graph around, reflecting it up, reflecting it down. We can talk about it being an increased rate of change. And this is really valuable because it just reinforces that all the rules that students have learned through the exploration of quadratics actually apply to all function types. Now, one of the biggest misconceptions for students is that A makes parabolas thinner. This is categorically wrong. What's actually happening when you look at the value of A is that functions are increasing faster over the same interval. That's a very hard concept. So, one of the best ways to actually explore what A means is to look at step functions. So, let's go ahead and change this from an absolute value to a floor function. So I'm going to go ahead and I'm going to reset everything. I'm going to put A at 1. I'm going to put H actually at 0. And I'm going to put K at 0. I'm actually going to change some other aspects of the graph to make it easier to see. Because with step functions, you're really just looking at those line segments, which can make the graph a little bit harder to read in many situations. I'm also going to change the color of the graph. There we go. All right, so one of the things that we've said is that students often perceive that A makes parabolas or absolute value functions thinner, and we've emphasized that that's incorrect. So let's test out this hypothesis. If A really makes things thinner, then these line segments that are graphed should get closer into each other as I change the value of A to be something greater than 1. If I have something between 0 and 1, these segments should get fatter, they should get wider. So let's go ahead and test it out. I'm going to change A to an integer value. Before I do, just take a careful look at the screen and see how things are spaced. 1 across, 1 up, 1 across, 1 up. Let's change that A to 2. Now here's something interesting. We've actually changed A to 2 and the function hasn't gotten thinner. In fact, each of these segments is still 1 unit across. What's different is the spacing between the steps is now 2 units. So in fact, A is not making anything thinner. It's actually making the spacing between each of these increments taller. And this is directly related to all those conversations about quadratics not actually getting thinner, but getting taller over the same interval, growing faster over the same amount of domain interval. And with this, we can actually start to explore lots of different things. Students may actually say, well, how is it that you make things thinner if A doesn't do that? Now, this is going beyond the scope of the Algebra 1 curriculum, but if students are interested, we can now put in B times X, add the value of B, and we can now note that B is what makes things wider or thinner. So we're going to go ahead and leave that behind. And with all of that, I'm going to be providing a bunch of different Desmos graphs in the classroom in my MCPS. But I hope that this video helps teachers create classrooms where students explore math, observe patterns, and develop conceptual understanding. If you have questions or comments or a video idea, please email me at the address below.